Okay, looks like everybody is settled in. Are there questions from last week about Spark? The things we covered last week? Yeah.
Right. So you started with your you put on the test dimensions, and you were showing that you were sitting show, having show,
Hmm.
and that was it. It's actually doing the transformations, right?
Yes.
And was you showing the hip show.
Yes.
You'll show how many it shows us like headbands and videos, or then we have too much data to see. Can you still use shows?
Yeah. So it'll automatically truncate the output based on whatever limit you pass into it. So I think the default is like 20 rows. And the default is not only to truncate the rows, but to truncate the columns. So if the column is too long to display, it'll kind of cut it short and replace the rest of it with three periods at the end, which is annoying. You can turn that off. Yes. It's don't truncate the columns. The rows still have a limit, but you can change what the limit is. So the default is 20. You can pass in 50 or 100 or whatever. And so that's sometimes what I do is I'll show 500 rows, turn off my cluster, and then spend the next 3 hours looking at it to see if I did was correct. That is a question I do not know the answer to. It could be cached, but that's mostly defined by AWS. So AWS, you're talking about S3, has an access tiering system. Um, let's see this. Okay. So we're going to be using Amazon S3 for all of our data store. Depending on how much you're willing to pay and how quickly you need the object. So where's the list of the tiers? It's around here somewhere. Um, Infographic. Just want the list of performance chart. That's what I want. Okay. And so the general rule of thumb is that you can trade the object retrieval latency for the cost that it takes to store something. So the lower latency you want, the higher cost it'll take to store that object in S3. Um, Whether or not it uses a cache, I guess it's up to an interpretation of what you define by cache. I believe what intelligent tiering does is for objects that are frequently accessed, it'll move them up a tier so that you pay more for the storage, but it will also retrieve it with lower latency. So it can have that automatic tiering for you, so you don't have to set it yourself. But there's intelligent tiering, and then there's standard, which offers the lowest latency, but it goes all the way down to Glacier S3 Glacier Deep Archive, which stores things at a fraction of the cost that normal S3 does, but the latency is like 12 hours to retrieve an object. I'm not sure why it's that long or what they're doing in the background to make it that long. Maybe they like disconnect the physical hard disks from the machine it's supposed to be stored on and put them in a freezer somewhere, and then somebody has to physically get them out. I don't know. Amazon does crazy stuff like that all the time. They have this service called, I think it's Snowmobile. And this AWS service, literally what it does is it drives over to your data center, loads all of the SSDs into a truck, and then drives them to an AWS data center. That's an AWS service because it's literally faster than transferring it over the internet. It's, it's so funny. That's how I think that's also how Google, when it's maintaining its indices for its search engine, actually moves huge amounts of data. So they don't move it over the internet. They just drive. The internet's too slow. That's what they mean by the bandwidth latency trade-off. It's high latency and high bandwidth. But does that answer your question? Okay. And then there's pricing. Oh, okay, here we go. Pricing. Let's see what the pricing is for all of these different storage tiers. Free tier, that's not interesting. Okay. So the standard rate is about what is that 2.3 cents per gigabyte per month? And that's just the standard. And it gets cheaper and cheaper as you go down. And as you go down, the latency also gets higher. So you can have intelligent tiering, which, also increases and decreases the latency based on how much you access it. And then there's S3 Glacier and S3 Glacier Deep Archive. S3 Glacier Instant Retrieval for long-lived archive data accessed once a quarter with instant retrieval in milliseconds. How is that different from just standard? What? Maybe. But like they would still need to keep it ready for you. You'd think that's what the primary cost is. For each object that is stored in S3 Glacier Flexible Retrieval charges for 40 kilobyte of additional metadata for each archived object. There's a minimum billable object size. Okay. Well, anyway, any questions on how the tiering works? We probably won't be interacting with this very much because we'll mostly be using S3 to directly interact. So we would want, latency in at least seconds. So we wouldn't be interacting with deep archive or anything like that. So it would just be standard too. Okay. So has anybody experimented with using EMR at all or EC2 or anything since we talked about it last week? Well, we didn't talk about AWS last week, but okay. So the main three services we'll be using in AWS are EC2, S3, and EMR. EMR is what actually is responsible for managing these Spark clusters that you're going to spin up, and it manages tearing them down. And it also manages all the custom stuff that's put in these EMR clusters that isn't in a normal EC2 instance. So it comes with stuff like a Spark distribution, and there are certain instance types like on EC2, and we'll go over that in a second, that have different storage capabilities. And so depending on the storage capabilities, it will change where certain devices are mounted and things like that. And S3 is for data storage, and it's the permanent data storage that we'll be interacting with alongside the temporary storage that exists within EMR. Cool?
Yeah, it's been long, but cluster of EC2s.
Yes. Yes. An EMR cluster is a cluster of EC2 instances. So if you spawn a cluster on EMR and then you go to EC2 and you look at all of your instances in here, then they will show up. So they are EC2 instances that are managed by EMR. And there's a very, very small additional cost to using EMR, but like 99% of the cost of using EMR is just EC2 and that uptime. Okay.
So if you were to use just straight EC2, you can still use a lot of instance, right? When we're getting first,
Yes.
still use distributed processing that way.
Yeah. So that's what the data scientists at Count do is a lot of the time what they'll do is they won't actually use Spark as a distributed system at all. And they will only use like a single large machine to execute all their code. So if we look at the EC2 instance types, we have all of these different instance types available to us, and they're optimized for one of those instances. That's a big instance. It has almost 100 cores and 400 gigs of memory. So it's a big instance. Um, but the interesting part is that you can increase the number of these instances that are on the cluster, and you might decrease the size of the instances, but increase the number. And maybe you want to do that to, increase the fault tolerance. Like if one of your instances dies, then it doesn't impact the whole process. Because that happens from time to time, is when we're running our identity linking process, it's a big, heavy process that takes 12 hours to run. And sometimes the processes or certain EC2 instances just die and become unreachable for whatever reason. And you can configure Spark to replicate its data storage and say, okay, you're going to store these partitions of the data on two machines at once. So then if you lose one machine, the other machine has a backup so that when you replace it, you can move all the data back over. And I'll tell you guys how to do that pretty soon. All right. So you can spawn an EMR cluster using a bunch of different types of EC2 instances. And you can go over those right now. Yeah, let's just go over them right now. Okay. So the first type of EC2 instances are the general purpose instances, and that is what the data scientists at Count tend to use when they're running their analysis. I don't normally run these. And the reason I don't normally run the general purpose, and I also don't normally run the compute optimized instances, I usually run memory optimized. And basically, the only difference here is the memory capacity between all of these things. So if you look at the general purpose, right, we have a ratio of memory to CPU count we have about 4 gigs of memory for every CPU. And that extends all the way down to the larger instance types. So we have 4 virtual CPUs and 16 gigs of memory. So that's 4 gigs per CPU. And that extends all the way down to here. It's, 96 CPUs and 384 gigs of memory. When you go down to compute optimize, it's the same concept, except the ratio is different. So the ratio is, 2 gigabytes per CPU instead of 4. And that's basically the only change. And it means that compute optimized instances are actually cheaper to run than general purpose for the same CPU count because they just have less memory. There are other modifiers on different instance types. So you can see this C7G marking. Everybody's seen that. These are kind of small. You can see this C7G marker. And what that means is this is a C-type instance, so it's compute optimized instance of the 7th generation. And the G-type refers to the fact that it uses AWS Graviton 3 processors. And the reason this is relevant is because there are 2 computer architectures available to you when you want to start up an EC2 instance on EMR. There's ARM, there's 64-bit ARM, which is what x80, or not, which is what AWS uses in its Graviton processors. There's also 64-bit x86, and that is the architecture that comes from Intel and AMD. And for most cases, it doesn't really matter which one you use, but it matters to us And the reason it matters to us is because we have a special library that comes from a company called Melissa Data. Melissa Data, what their job is to take an address, like a postal address, and standardize it. So we give it a postal address and they put it in the standardized format. And how they do this is they send us a big blob of data that's about 30 gigs that has a record of every single deliverable address in the United States. That's about 30 gigs. And they also send us a pre-compiled shared object Linux binary. And that is compiled exclusively for x86. So every time we want to use Melissa data, we have to use x86 architecture. And that comes up more often than you would think. But for the most part, in this class, it probably won't matter which one you use unless you're doing something like really hardware specific in your UDFs or something. I would recommend that you use the G-type instances instead of anything else. These instances tend to be cheaper and they don't really offer any downsides in comparison to other instance types. So something like the C7A, which is, 7th generation compute optimized, but instead it uses AMD EPYC processors instead of Amazon's Graviton. And these are more expensive to run. So if you look at the pricing, they charge, or they don't charge by the hour. They list the charge by the hour. I think they charge. The cheapest one, the cheapest generation actually seems to be the C6G instances. So for the same size, they're a little bit cheaper than the C7s, which is nice. But you can also see that for the same size, it looks like the C7As are about 50% more expensive per hour. And that makes a big difference. So unless you have a specific reason to use x86 architecture instances like the C7A, use ARM. So use the G types. Any questions on that? Okay. There's another modifier that we need to be aware of called the D-type instances. So D-type instances have local SSD storage available to them. So if you see the instant storage on these, they'll say, oh, this instant storage is EBS only, and it's EBS only all the way down. Okay, so the C7As only have C7As only have EBS only. Okay, so the C7Gs have D-type instances available to them. And the difference between the two is that these D-type instances have local SSDs attached to the physical machine that you're running. And one of the biggest reasons this is useful is that it significantly improves your disk read latency. So if you need to read or write to local disk, that's a significant improvement if you're using the D-type instances versus EBS volumes. So EBS volumes, they act kind of like disk. It's abstracted away. So they act like a local disk, but they're actually, transmitting over the AWS network somewhere. And one of the key differences between EBS storage and local storage is that EBS storage is permanent, unless specified otherwise. So you can allocate an EBS volume and you can read and write to it as much as you want, and it'll still be there if you kill your instance. That is not the case with your local instance storage in a D-type instance. If you, halt your EC2 instance or you terminate it, then that data that you stored on your local storage will not be available to you anymore after you kill your instance. Questions on that?
Yes,
Elastic block store. And I believe that refers to the fact that a file system will store your data, your files, like physically, using blocks. So these blocks are separated into, I think it's usually 4 kilobyte sizes. So every file can be or is separated into like 4 kilobyte size chunks. So I think that's what it that's the origin of that. Okay. Questions on the D-type instances versus EBS? And this has also been relevant before. This is actually one of the key changes that between normal EC2 instances and EMR instances. So EMR will do some, will create some special changes to these EC2 instances to make them easier to use automatically. What I was doing is for your projects, I'm trying to get hold of the Wikipedia data set so you all can do analysis on the entire Wikipedia data set. And I think that's going to be really cool for your projects. But let me tell you, it is a huge pain to deal with. We're going to talk about this later, but Wikipedia is the perfect example of how to not publish a data set. It's horrible. And something I was doing is Wikipedia stores everything in MySQL tables. And MySQL tables, they can become quite large. And so when I started the MySQL server on the EC2 instance I was using to process the Wikipedia data in a form that you guys could actually access, I did not realize that MySQL was actually using my EBS volume instead of local storage that I had provisioned. And so midway through the database import, it failed and it says, oh, I don't have enough space anymore because the EBS volume had filled up. So I had to restart the entire import because I had pointed it to the wrong storage. That was a fun time.
So we have the system, you also have to do it.
Yes. So every instance comes with an EBS root volume, and that's where the operating system is stored and other permanent files. I'd say it's still elastic because I believe you can change the size even after you create the EBS file. So let me see. But I think you have to provision it beforehand. Let's check, actually. That's an interesting question. Oh, there we go. It is. It's not in some tab. So what happens if you create a volume? I'm cheap, so let's just do 3 gigabytes. You don't need to create it from a snapshot. All right, let's create the volume. This is creating an EBS volume. Oh, that's the storage type. So it still has to be like physically stored somewhere. And you can pick the storage type depending on what your requirements are. Maybe you want it to be super cheap and you don't care that much about the latency. Maybe you're trying to do like exclusively sequential access because that actually matters when you're writing code or when you're doing certain things. So, or maybe you want random access. It really depends. So like, let's see if we can modify. You can modify the size. Look at that. But you still have to provision it. If you're extend the file system, you only do this. Okay. If you're increasing the size of the volume. Interesting. Okay. So it looks like I'm not gonna read this live in class, but it looks like there are some limitations on exactly when you can resize an EBS volume. But this has also come back to bite me a few times because we had issues in the past where we needed to access these, Melissa data standardization files on EMR. And we had a problem where when we were downloading them with EMR, instead of writing to local storage, they were writing to the EBS volume. And the EBS volume is way slower. It's way slower to write to, and it's way slower to read from.
So, it's also.
Yeah, yeah, because there's no guarantee that it's actually on the same machine. So local storage is, guaranteed to be on the same machine. Oh, that's interesting. So there are all sorts of volume types you can use. Okay. Questions on the volume types? This is going to become relevant if you create processes where you need to spill some of your data over to local disk. That is much, much faster when you're using instances with local storage. So if you're using instances with local storage and you load it into EMR and the amount of memory you have isn't quite enough to fit everything, that's okay. It can still spill over to local disk. But that access is much faster when you have local disk and it doesn't have to use EBS. Make sense? Cool. Okay. Oh, this is the pricing too. All right. So for the memory optimized ones are are pretty much the same as the general purpose and the compute optimized instances, except they too have a different virtual CPU to memory ratio. So this one has an 8-to-1 ratio, which is why when I'm programming in Spark, I normally use memory optimized instances because compared to CPUs, memory is cheap. And when I'm having performance problems in Spark, a lot of the time it's due to the fact that I don't have enough memory. Seriously, fitting everything in memory is the biggest contributor to having good performance in Spark. If you can fit everything in memory, everything will go like that. It's so fast. And there are actually different ratios in the memory optimized category. So this one has a 1 to 16 memory to CPU ratio. And I've never used these X2s in EMR, but I have used X2s in other work that I've done at Count. And some of this other work required, only 3 cores to run, but I needed like 200 gigs of memory. So I used an X2 instance for that. Questions on those? Okay. Now, these are the types of instances that we're probably not going to use. The accelerated computing instances have GPUs available to them. So unless you're doing something pretty special, we're probably not going to need these. I don't even know if you can use these on EMR. We should check. I've never used them on EMR, but let's see. Let's do West 2. That's where we are. Compute optimized, memory optimized. Storage optimized. That's weird. So apparently you can't use them. Anyway, never mind then. What I just said wasn't relevant. You can't use these anyway. All right. Now, lastly, we have storage optimized instances, which I have also never used. And these have a disproportionately high number of available local disk space to them. And that's particularly helpful when you need to run, something like a database, something that's not an in-memory database. So if you're running something like Redis, then in a storage optimized instance may not be a good idea. But you could run a storage optimized instance for like a SQL database somewhere. So you could just spin up one of these. And for the amount of storage they provide, they're pretty cheap. Like these i3 type instances, have only 2 CPUs and about 16 gigs of memory, but they have 400 gigabytes of available SSD available to them. And, compared to the memory optimized instances, these are about like a third of the cost for the amount of storage that it gets you.
Per CPU.
No, that's total. Okay. Questions on EC2? All right, let's talk about S3. All right. So for S3, what I'm going to have you all do is you will all create like a workspace S3 bucket for you to be able to read from and write to. So EMR, you'll be able to create, data sets in EMR and then write them to your own S3 bucket. This S3 bucket is special because every one of you is going to be able to read from it because that's just how I'm going to provide the data sets to you. You won't be able to write to it because it's mine, but but you can read from it. And this is the data set that I'm planning on giving you, which is Wikipedia, which is partially in here. So right now I have the links between pages and a couple of other things. So it's getting there. Hopefully by next week I can import everything. It's taking a while because Wikipedia is stupid. So how this works is you can see that it kind of looks like a file system. Don't be fooled. This is not a file system. This is not a hierarchical structure. And the reason for that is if you want to take a directory looking thing like Wikipedia and see it how it has a bunch of subdirectories, these aren't actually subdirectories. This is the UI lying to you. What actually happens is you have this idea in S3 called a prefix. And so this has nothing to do with this prefix word right here. The prefix is everything that comes before the end object. So the end object here is, data underscore aa.json.gz, which is a gzipped JSON file that has one JSON object per line. And, Spark / EMR can, interpret these fairly easily. But if you copy the URI that refers to this object, you can just copy it here. You'll see that, it has this S3 qualifier in the front, and then the name of the bucket, and then it has this prefix within the bucket. So this prefix, even though it looks like a file path, is a singular prefix in the sense that if you wanted to find, everything that is within the Wikipedia path. Yeah. Okay. A bit more. How's that? Okay. So if you wanted to find everything that's within the Wikipedia path, you would basically have to look through everything in the entire bucket because it doesn't hierarchically store anything. So what it does is this is probably off topic for this class, but for every prefix, it tracks every prefix individually per prefix. And there are limitations on the amount of stuff you can read and write to and from every prefix. But you can read and write from any number of prefixes simultaneously as much as you want. That signifies to me that there is some co-location going on where everything within the same prefix might be stored in a similar place. That's what that signifies to me. And so you can easily list everything that occurs within the same prefix, and you can quickly retrieve everything that occurs within the same prefix because that's how it tracks it. It's almost like a hash table, or it's almost like a dictionary where the key in the dictionary would be actually just where the key in the dictionary is literally this entire prefix. And the value is, another list of objects. So the value is CGZ. This is kind of how it's structured. So the entire prefix acts as the key. So if you're going through, a dictionary and you want to find, you know, um, slash, link target, which is another one of the prefixes in here. So if you want to find stuff under link target instead, then that's a completely different key. So in this dictionary, you can't just tell the dictionary, hey, list everything that starts with dataset slash Wikipedia. You have to go through the entire dictionary to find all the keys that match this pattern, because that's not how a dictionary is structured. You could do it in a B tree, but you can't do it in a dictionary. And so S3 works in very much the same way, where, just because that two prefixes share a common path in their name doesn't mean they have anything to do with each other internally in the system. Good? Good. Okay. So S3 will also encrypt things for you automatically using, wait, I have to go to show you that. There's encryption. So it has server-side encryption automatically available for you. So if you're working for a company that has pretty strict security requirements, you can tell Amazon to encrypt it themselves. Or if you really like pain, you can manage the encryption manually if you like pain. Okay. Are there any questions on S3? It's a pretty simple service. There's not much explanation it needs beyond the storage tiers and the prefix structure. Questions on that? All right, let's start an EMR cluster. Yeah, it's record. Yep, there we go. Oh, you can see the graveyard of all the previous clusters that I've spawned. Let's just clone this guy right here. All right. So what we're gonna do is we're gonna pretty much exclusively do okay, I didn't see that. I should explain this first. Okay. So you can choose uh what other software you want bundled into your EMR cluster. Now, what I've done here is I've selected the minimum that I would need to run a cluster, and it's not very much stuff. So this is Spark, and it automatically comes with Spark. The Spark version is 3.5.1. The most recent release is 3.5.2, and EMR has a history of letting their Spark release kind of lag with the official latest Spark release, which can get annoying, especially if the latest Spark release has either performance improvements or extra features you want. So keep that in mind. Keep in mind that EMR can be a little slow to update this software. Now, the interesting thing is by default, Livy is enabled. Now, Livy is a piece of software that supposedly not supposedly it does, that allows you to connect to an EMR cluster through a notebook using a special type of Python notebook kernel called Spark Magic. Now, I don't want to use this because if you go and look at Apache Livy, like, it is not a well-maintained piece of software. Assuming these people are using semantic versioning, they've been in business for 8 years. They've been developing this for 8 years, and they still have not had a stable release. I don't know why this is true. I don't know why this is the case, but we've had other issues with Livy where they're not compatible with certain Python versions. And what we have to do is we would there was a point now where I had to go in to Amazon EMR, delete Livy, manually reinstall it on a newer version, and then make some changes in that code to get the thing to work. I do not want any of you to have to go through that pain. So what we're going to do instead is I want to use Spark Connect in this class. And Spark Connect mostly does everything that Livy is capable of doing, but it tends to be easier to manage. The logs for Spark Connect are easier to access, and so it makes debugging a lot easier. And you don't have to go through the pain of having Livy problems. The one downside that I've come across when using Spark Connect instead of Livy is that Spark Connect doesn't allow you to use Spark's older APIs. You can only use the new ones, which the vast majority of the time isn't a problem. There's one feature that I need from the old API that the new one doesn't have. And I don't think the data scientists have ever had to use it. So at least in my experience, and that tool is called map partitions, by the way. In my experience, map partitions has been an exclusively engineering tool. Questions so far? I don't even want to look at this thing anymore. Okay. So we don't want Livy. Go away. So what we're going to do now is we need to choose an instance type. So you need to choose a primary, which is the coordinator node in the cluster that's responsible for keeping track of all the other nodes in this cluster. And this primary is your entry point into the cluster. So if you need to SSH into it for whatever reason, or when you just connect to it with Spark Connect, you connect to it through the primary node. Okay. So now you can, and the primary node doesn't actually like do anything. So you can select it to be the smallest available instance type, which is a C6G. So for the core nodes, these are the nodes that do the actual work. So depending on what your requirements are, you may need to change this. So there's C6G available to us. We can also create an R6G instance type of a bunch of different sizes. Let's actually just do C6G for now. Let's do C6GD. So I want some local storage. And that'll be extra large. And let's see, how many of them do we want? Let's do 4 of these guys. Oh, this is what we were just talking about. So this is the size of the EBS root volume for all these nodes. Now, because I specify that these are D-type instances, we're not going to need EBS size to store any of Spark's data. So the only thing this would be for is storing like the Spark code itself and the operating system and a couple of other things. So you don't need a large EBS volume in order to run EMR. And so it doesn't really matter like how much data you're working with in EMR. The EBS volume doesn't really affect that especially if you have local storage. Questions on that? And I prefer to set the cluster size manually because I don't trust Spark to do anything right. You can also create bootstrap actions. And so these are scripts that you can run that run every time every instance starts up when you start the EMR cluster. This is particularly helpful when you need to install special dependencies or download data files that your program needs to use. We use bootstrap scripts to have Melissa data on EMR. So we take Melissa data, which is that, giant 30 gigabyte file with all the US addresses, and we download it onto every node in EMR so that when we do our processing and we need to standardize, a billion addresses, we can do them all in parallel and everybody has access to a local copy of that data. So we use the Bootstrap scripts to download that data before any of the processing starts. Cool? Cool. All right. So you also need to configure your EMR cluster, and that's just a JSON object, which is a list of different configuration options. And these are the configuration options that I use. I will share this with you all. I don't think you will need to change this during your time taking this course. It's very simple. So the only things in here are this maximize resource allocation flag. This is exclusive to EMR. And what this does is it will look at your cluster configuration and it will look at the nodes in the core group. So we saw in the core group that we set earlier, we said we had 4 C6GD extra large instances. So what it will do is it'll look at the resources that those machines have, and it will set how much Spark is supposed to allocate based on what's available to it. So that's what maximize resource allocation does. And this one is also a little strange. So what I've been getting lately, and this didn't used to happen, is I will have sessions that will fail because of this log4j hot patch flag. I don't actually know what this does. It's some dependency somewhere that EMR has not properly updated. And maybe like 30% of the time, my sessions won't start because it will not have this hot patch jar available to it. So this is just there, just so you know. I don't know very much about this flag, but I do know that a small percent of the time, it will not start unless I have this disabled because apparently it didn't download it from somewhere. All right. So what this is this will tell the system to compress your data frames when they're in transit. And what this will do is this will set the serialization algorithm that Spark uses to transport data, to and from machines or between machines. And it will also determine the type of format used when it's just storing data, like in memory, because you can decide whether or not data is stored in a serialized form or in a deserialized form, which is nice. And lastly, what this is for, okay. So about 2 months ago, my team and a couple of other people got on a call with the folks at Amazon who are in charge of EMR. And I had about 30 different questions to ask them about why certain things didn't work. And one of the things that doesn't work is if the object, this probably won't come up in this class, by the way, but I put it here anyway, just in case it does, is when file uploads to S3 get large enough, S3 actually splits them up into multiple pieces to upload in parallel, and that doesn't seem to work with EMR. And so what I've done is this number sets the threshold that if the file size is greater than this threshold, then it'll split it up into multiple pieces. This threshold is the largest it can possibly be. This is a 5 gigabyte threshold. If you're uploading a single file to S3 from EMR that is 5 gigabytes, that is too big. Squash it down. Any questions on that? I know this looks stupid, and it is stupid, and it's pretty weird that it has to be there. But I spent like 2 days trying to figure out why this wasn't working, and I couldn't figure it out. So eventually I just turned off multi-part uploads using this, because that was the solution for some reason. And again, this probably won't come up because hopefully you will not be uploading files to S3 of a large enough size to even trigger this behavior. But I figured it was kind of cool to talk about it anyway. Because it's really dumb. Questions on the software settings? Okay. All right. So now what we need to do is we need to configure an EC2 key pair. And this is so we can SSH into the primary node to access it. That's how we're gonna use Spark Connect is we're gonna connect to it through SSH tunneling. Because that way we don't have to set up any complicated security group rules. We don't have to set up any network rules. We don't have to set up any, special, ingress criteria or anything like that. We can just use SSH tunneling. It's very simple and it's nice. So we don't have to do any extra configuration if we use SSH tunneling to directly connect to the EMR primary instance. So I've already created a key pair. So I am just going to use that. Okay. So what you also need to do is you need to create what's called an IAM role for Amazon EMR. And what an IAM role does is it gives permission to EMR to access things like S3 and to start the EMR cluster in the first place. I actually forgot about this, or I would have shown you IAM earlier. So if we look at IAM and we look at the roles, we look at which ones are we using? We look at the service role and the instance profile. Instance profile will. And the service role for EMR cleanup. Is that what that is? Okay. So we can look at the permissions that are given to us by that I'm giving Amazon EMR with this role is we are allowing these actions. And these actions are all just relevant to S3. It's so it can read and write to S3. Can you see this? Is it too small? Is that better? Okay. Okay. So you can look at these permissions and decide which ones you need and which ones you don't need. I've basically allowed it to do anything it needs to do with S3 in order to access the data it needs to perform its analysis. So that is the instance profile IAM role that we're going to use here that allows all of the core nodes, the worker nodes, to access S3. That's pretty much the only thing they need to do. That's the only permissions they need. The service role requires other permissions. So the service role it's to allow the EMR cluster to, even be created in the first place. And I honestly think that AWS will just create one for you if you need it. And you can select all of these things and yeah, honestly, it will just create it for you. Yeah. I don't think you need to worry about IAM stuff too much. It is really easy to go down a rabbit hole and wind up in permissions hell where everything's broken. So I prefer not to mess with this if I can avoid it, because that's a huge time sink. But a lot of the time it'll just create them for you. And I honestly think that's how these roles were created, is I just automated it. Amazon will just do it for you. And luckily you should have permission to create roles. Ben Peterson and I had done quite a bit of back and forth on how we could create roles for all of you to use and such and such. And none of that wound up working. So all of you have permission to create your own rules. And so you can create the service role just using this. And I think you only have one VPC or one subnet to use anyway. Questions on that? All right, let's start it up and then connect to it. And this takes about 5 minutes, so we can just sit here and twiddle our thumbs or talk about something else if we want.
Downloaded the information. What is it on this machine?
Probably just to downloads. The downloads folder. Oh, you can put it anywhere. Yeah, so you can, whenever you SSH into the machine, you just reference the key file somewhere, wherever the path is. Yeah. Connect to the primary node using SSM. What on earth is SSM? Social security, social security machine? Wait, it says SSM over here. Like, can I not read? Is this not an M? Okay, wait. So this is connecting to the primary node using SSH. This is connect to the primary node using SSM. But if I click this, it goes to the SSH tab. What is going on? Okay, whatever. We're not going to worry about this. It's on you and your silly, silly things. Okay. All right. Now let's SSH into the, wait, I don't think we can right now. No, we have to wait. It's still provisioning. Is there anything else we want to talk about for the next 3 minutes? Well, don't everybody start talking at once. Yeah. So when you have a bootstrap action, this particular cluster doesn't have any bootstrap actions, but you can create a script like a bash file that you could upload to S3 and then reference when you're creating a bootstrap action. And that will run on every single machine when you start up the cluster. So you can use it to download files and put them in the right places and download, kit packages or whatever else you want. I feel like I'm waiting for something to come out of the toaster. This takes like 20 minutes at count. We should feel lucky. Huh? 40? It's gotten worse. Oh, oh dear. Oh no. Someone should take a look at that. That's awful. I bet it's because of the Equifax network. Just blocks everything. Takes 5 minutes to reach out to Google Mail. it's a slight exaggeration, but every time I download something, it takes like there's like a 3 minute delay between when I click on the link and it actually starts downloading when I do it from my work VPN. It's horrible. This was my daily routine for a few months. Just wait 20 minutes for EMR to start up. I could start the EMR cluster and then there it is. Okay. The Pop Tarts are out now. All right. So now, yay. All right. This is what EMR looks like. And you can't see anything because it's too small. Why is it increasing the size of the window? That's okay. You know what? I don't even have the energy to complain about it right now. Just, what do you even, why? Why would you do that? Such a weird way to implement your text scaling, whatever. Okay, so let's do some exploring a little bit. We can kind of roam around. So if you look at, which directory you're in, it's, slash home slash Hadoop. So in order to use Spark Connect, we have to actually start the Spark Connect server. And I forget the actual command that we need to do every time. So we're gonna cd into the directory that actually holds all of the Spark stuff. It's slash user slash lib slash Spark. You can see all of the wonderful Spark things in here. I believe what we're looking for is an sbin. Start Connect server. All right, that's what we want. I have to look up how to start the Spark Connect server because I forget every time. Here it is. Okay. So what we need to do is 3.5.1, not 3.5.2. And we need to actually point to the server slash sbin. Did the cluster actually start? Oh, getting ahead of myself. So wait, Spark class. Okay. I don't think the Spark Connect server is actually running. Okay. Oh, joy. Okay. So now what we need to do is I'm going to tail this log file and well, okay. Is that it? And then I wrote down the actual command that I use somewhere. There it is. Okay. tail dash f dash n one, and then the log file that this thing barfed at. Okay. So now what we need to do is we need to create an SSH channel to actually connect Spark. Just copy this thing. That is wrong. It's 15002. Everybody see that? That is way too small. Y'all need to tell me that it's too small. So everything I was doing over the last 10 minutes, nobody saw that. We need to go over it again. Oh, it was zoomed in like, oh, okay. Oh, thank heavens. Okay.
So what are you gonna see? Okay, so you already associated.
Yeah. So right now we're creating an SSH tunnel. So that's port forwarding. So the Spark Connect server is running on EMR primary node. And the Spark Connect server is accepting connections from port number 15002. And so what I'm doing is we're taking the 15002 port that is running or that is accepting connections on the primary EMR node, and we're forwarding it to our local machine. So that way, when we connect to, localhost 15002 on our machine, then everything we send to that port actually forwards to the EMR node, to the EMR master node. So that's the port forwarding that we're using right now. Yeah. That's the default for Smart Connect. Okay. So, oh, I actually have something right now. Something running right now. Okay. So we can just run that. And hopefully we can just create a Spark session. See if this works. Did we get... Did it actually work? Okay. So let's read some data from S3. So let's do spark.read.text. And then we can take any path from S3 that we want. We'll just read the William Shakespeare stuff again. We'll copy the URI for that directory, or not directory. I should not have used that word. Spent 5 minutes explaining why we shouldn't use that word. Okay, and just do a dot show. There we go. It actually ran. Look at that. So we are connecting to a Spark session in EMR, retrieving data from S3 and printing it out. Oh, joy. We did it. Okay, we're basically at time now, but that was fun. Took us an hour to get here when we got there. Does that whole setup process make sense to everybody? So we have another hour for questions because it's office hours right now. Um, yeah. Okay. Yeah, can we just redo the whole lecture, please? That'd be great. Yeah, yeah, all yeah.
You had the first is actually to your if it is an SSH and you first did the path to Word.
So yeah. So let's break this down. So we're SSHing. We're using my key. This will be different for you. So you're going to need to create your own EC2 key pair, and it'll automatically download for you, and you point it to the PEM file. So what this means is that instead of creating a shell, what we're going to do is we're going to create a port forwarding. So that's the -L option here. So the -L option says we're going to create this port forwarding. And this is the actual thing that we're SSHing into. Most of this you can just copy from the primary or from the AWS console. So you can copy this. 90% of it is here. The only part of it that isn't here is the port forwarding. So this bit. So when you start up a cluster, there's 3 things you need to do. You need to SSH into it. You need to start the Spark Connect server on the EMR primary node. Then, this is not required, but is recommended, is you need to, or you should, set up a live feed for the log file that the Spark Connect server is using. So if you have any problems, you can just read it right here. It's a lot of stuff, but it's better than not having access to it at all. And it's an absolute pain to find when you're using Livy, but when you're using Spark Connect, it's right here, which is really nice. So I would highly recommend running, this live feed for the log every time you start up an EMR cluster. So that's number 3. The 4th thing you need to do is to set up port forwarding. And then you should be in business. Because without this, the code on your notebook or wherever you're connecting it from won't know where to connect to. Because without this port forwarding, localhost 15002 doesn't actually exist. So it's kind of like the port forwarding goes to, let's say, this is the nope. These horrible markers. Where's the black marker that we were using last? Okay. So you have your notebook, you have your laptop, or whatever machine you're using. Then you have EMR running in the background or running in AWS. Okay, so EMR is accepting connections on port 15002, and those are going to Spark Connect. What this needs to do is your notebook is connecting to localhost 15002. That's the address it's connecting to. But localhost refers to this machine, not EMR. So what this machine needs to do is it needs to take this port, this 15002 port, and basically copy it. So everything that gets sent to 15002 on localhost actually gets sent to EMR. So it basically sets up a middleman, so it forwards everything. Yes. That, yeah. So that's this. Yes.
Okay.
So unlike Livy, Spark Connect runs entirely on your machine. So it doesn't go through Livy at all. So there's no confusion between, oh, am I using the local magic for this cell and this cell doesn't use the local magic, so it actually executes on EMR. All of your cells execute on your local machine. All of them. So what this will do is every time you create a job, your Python will parse your code, read your code, and then Spark will kind of execute a shell version of that code that doesn't actually do anything, but it builds an execution plan and it sends the execution plan to Spark so it can actually do the thing. Building the plan happens on your machine, but actually executing the plan happens in Spark. Executing the plan is the expensive part. That's what takes all the compute.
So all my variables are local.
All of your variables are local. Yes, all of your variables are local. But remember when we were, creating like temporary views and temporary tables last time, those still live in EMR. Yes, because they're executed in EMR. Exactly.